Hello everyone, my name is Mark van Loosrecht and in this lecture we'll explore bioplastic production by microorganisms. Let's start with the basics. Bioplastics are plastics that are either bio-based or biodegradable, or both. So, some bioplastics are made from renewable biological sources but may not degrade easily, while others, like the ones we'll focus on, are fully biodegradable. One important group of biodegradable bioplastics are polyhydroxyalkanoates or PHAs. These are microbially produced polymers made from organic carbon sources. They can be used as a biodegradable plastic material that can serve as an alternative to oil-based plastics such as polyethylene or polypropylene. PHAs have similar physical and mechanical properties to conventional plastics, but with one major advantage: they can be produced from waste organic carbon. That means what we used to call waste can now become a valuable resource. So what actually are polyhydroxyalkanoates? They are storage polymers in bacteria. You can think of them as microbial fat. Chemically, PHAs are polyesters of beta-hydroxyalkanoates, which are derived from volatile fatty acids. The most common form is polybeta-hydroxybutyrate or PHB. Under the microscope, these polymers appear as bright, refractive granules inside bacterial cells. In fact, under certain conditions, these granules can fill up most of the cell's volume. Almost all bacteria have the ability to store some amount of PHA. They typically do this when growth is limited, for example when there's plenty of carbon available but essential nutrients like nitrogen or phosphorus are missing. In that case, bacteria cannot use the carbon compound for growth, so they store it inside the cell as PHA. It acts as a carbon and energy reserve, ready to be used later when conditions improve. In dynamic environments, like wastewater treatment systems, this storage capability is also crucial, despite all nutrients are available. During the so-called feast phase, when organic substrate is available, bacteria rapidly take it up and store it as PHA. Then in the famine phase, when external carbon is depleted, they use the stored PHA for growth and maintenance. This strategy allows bacteria to maintain a more stable overall growth rate, instead of growing very fast during feast periods and dying off during famine periods. So PHA accumulation is a universal microbial adaptation mechanism, particularly important in fluctuating environments. Now, how do we select bacteria that produce large amounts of PHA? In pure cultures, we can simply limit nutrients like nitrogen to stimulate PHA storage. But in mixed or open cultures, we use what is known as feast-famine selection. Here's how it works. Instead of feeding a continuous flow of substrate, we operate a sequencing batch reactor or a continuous mixed reactor operated in pulses. We periodically add a pulse of substrate, say once every hour. For a few minutes there's plenty of substrate, the feast phase, and for the rest of the cycle there's no substrate, the famine phase. Under these conditions we select for bacteria that can rapidly take up substrate and store it as PHA to survive the famine phase. Over time, bacteria that don't store PHA are outcompeted, while efficient PHA producers become dominant. Using this approach, we can create a biomass that contains up to 90% PHA by dry weight, a very efficient process. Interestingly, the substrate type determines which bacterial species dominate. However, because the biochemistry of PHA synthesis is highly similar among microorganisms, the end product and overall process kinetics remain quite similar. This means we can use different organic waste as feedstock, even those with variable composition. And the microbial community will adapt naturally to the available carbon sources while the process remains stable. Let's look at a real example of PHA production developed at our university, now commercialized by Parks Biomaterials under the product name Kaleida. Here's how the process works. First, organic waste is fermented into volatile fatty acids or carboxylates. These fatty acids are then fed into a feast-famine bioreactor where we select bacteria with a high pHa storage capacity. The resulting high pHa-rich biomass, containing up to 90% pHa, is then transported to a pHa extraction facility. The enrichment can be done on-site, near local wastewater streams, while the extraction can take place at a centralized facility. Finally, the extracted Kaleida PHA can be supplied to the chemical industry to produce bioplastic materials. This approach can even make industrial processes circular. Take the example of a paper recycling mill. Such a mill generates wastewater rich in organic carbon. By using PHA-producing organisms, that organic carbon can be converted into PHA in a feast-famine process. The treated water can then be reused in the factory, while the PHA can be extracted and converted into coating material or adhesives, used again in the paper recycling process. In this way, all the organic carbon, even the waste, ultimately returns to the recycled paper, creating a closed-loop system. Municipal wastewater treatment plants also naturally experience feast-famine cycles. During the day, they receive high loads of wastewater and much less at night. Because of this pattern, the microbial community in these systems already accumulates PHA to cope with this alternating substrate availability. So the activated sludge from such plants can be used directly as a PHA accumulating biomass. By combining organic waste fermentation to produce volatile fatty acids with the PHA accumulating capacity of this sludge, we can produce PHA-rich biomass that can then be extracted into bioplastic materials. Let's compare the two main approaches: direct accumulation in waste-activated sludge and enrichment cultivation for specialized PHA-producing organisms. In the direct accumulation approach, the process is integrated into the existing wastewater treatment system. The type of organisms and the PHA yield depend on the wastewater composition and treatment conditions. Typical PHA content reaches 30 to 50% of the biomass. In contrast, enriched cultures are operated separate under controlled feast-famine cycles, leading to much higher PHA content up to 85 or 90%. Both methods use waste-derived feedstocks, such as industrial wastewater, municipal wastewater, or even fermented organic solid waste. Industrial and organic waste streams are especially suitable because they often provide high concentrations of volatile fatty acids. To summarize, polyhydroxyalkanoates, especially PHB, are storage compounds produced by many bacteria. They are not part of normal cell metabolism, but accumulate under nutrient-limiting conditions or in feast-famine environments. Bacteria use PHA as an internal carbon and energy reserve, storing it when substrate is available and consuming it when substrate is absent. This allows them to maintain a balanced growth rate over time. By applying these selection principles, we can enrich highly efficient PHA-accumulating bacteria. It's important to note that we are not selecting a specific species, but rather a metabolic strategy, the ability to convert organic carbon into PHA. And since this metabolism is similar across many bacterial groups, the process design focuses on metabolic function, not taxonomy. In short, microbial PHA production turns waste carbon into biodegradable plastics, creating a sustainable and circular bioprocess that can help replace fossil-based plastics in the future.